Hello everybody, and welcome to the very first video of the semester. And before we dive into the first example here, I want to just say a couple of words about our calculus course in general. So one of the really big concepts in a calculus course is the idea of rates of change. We'll spend a lot of the semester talking about that concept. And so in this first section, that's going to be our focus, is just talking about measuring and estimating rates of change, and also at the same time reviewing some things like function notation and how we think about functions in units. Okay, so with that said, let's take a minute to read example 1 together here. So after t hours, the population of a bacteria colony is modeled by the function p equals f of t equals 35 e to the 0.5 t. And they're asking us when the population grows faster during the first 3 hours or during between 3 and 4 hours. So we're essentially being asked to compare the rate of growth at two different times. Okay, and let's take a minute just to notice what we're given in the problem. Okay, so they give us a formula for the function. Over here to the right, they also give us a graph of the function. And just to help us navigate our way through this, let's notice what variables are on each axis. So down here we've got time. That's being measured in hours in our problem. Okay, and then up here we've got population, which is just being measured in the number of bacteria that we're talking about. Okay, so I'm hoping that you maybe gave a little bit of thought to this problem before you started this video, and maybe thought about how you would answer this question. Let's run through a way that we might think about this. Okay, so let me clear away a little bit of clutter here. So I'd like to start by seeing if we can actually estimate the rate of change in the first 3 hours. And we could get started on that question by figuring out how much bacteria growth do we get in the first 3 hours. Okay, let's see if we can answer that. Okay, so the bacteria grows by, okay, and one way to express an amount of growth in mathematics is to use delta. Delta P, that represents change in P. We're going to try to measure the change in population over the first 3 hours. Okay, so one way you could do that is graphical estimation. If you go over to your function here, at time 0, number of bacteria, we could get that by estimating this point. It's a little bit less than 50, maybe 40 or 35. And then after 3 hours, number of bacteria is maybe a little bit bigger than 150, maybe 160 or something like that. Okay, we could estimate it, but we also have a formula for the function. We can find more accurately how much the function changes by substituting the 3 and the 0 into the function and actually measuring the difference. So f of 3 minus f of 0 would just mean we're going to take 3 and substitute it in for t, and then we're going to take 0 and substitute it in for t. Okay, there's a calculation that will allow us to measure more exactly how much population change we got. Okay, and now idea would be to go to your calculator and just figure out what these two numbers are. This first one turns out to be about 157, and the second one is about 35. I'm rounding off. And if you subtract those, what you're going to get is 122 bacteria. Okay, so that's how much bacteria growth we get in the first 3 hours. Okay, but how would we measure the rate of growth of the bacteria? They wanted the rate of change from us in this problem. So to measure the growth rate, we somehow need to figure time into the equation. How fast are we growing over time? So what we'll do to get the growth rate, we'll just take that change in bacteria that we found and divide it by the amount of time that went by. Okay, which I'll call delta t. So we're going to take the 122 bacteria and divide it by 3 because 3 hours went by. Okay, and if you do that calculation, you're going to come up with a number that looks like 40.6 bacteria per hour. Okay, that's the growth rate over the first 3 hours. Okay, now if you're wondering, where did that bacteria per hour come from that we have here? Those units come from kind of just looking at this fraction over here. P is being measured in bacteria and T is being measured in hours, so the units of that fraction would be bacteria per hour. Okay, so we have a growth rate for the first 3 hours. What about the time between 3 and 4 hours? Okay, well, we can kind of analyze that in the same way. Okay, or let's say it this way, between 3 and 4 hours. We can measure the change in population. This time, we want to measure the difference between f of 4 and f of 3. Okay, so we'll substitute those two numbers into our function. All right, and this time, if you go to your calculator and just estimate what those two, punch those in and see what those numbers are approximately, we get about 259 and 157. Okay, if you subtract those, you're going to get 102 bacteria. Okay, and so the rate of growth is going to again be the amount that the population changed over the amount of time that went by. Okay, so we'll take 102 bacteria and divide it by the amount of time that went by. Between 3 and 4 hours, 1 hour of time passes. So we're just going to be dividing by 1 and getting 102 bacteria per hour. Okay, and that's the growth rate between 3 and 4 hours. All right, so do we have enough information then to answer the question? They wanted to know, where is the growth rate the fastest? So what we're doing is we're comparing this number, the 40.6, and this number, the 102, and we can see that we're getting faster growth rate between 3 and 4 hours. Okay, so that's the answer to our question. I would like to add one thing to this discussion. These two numbers that we calculated, the 40.6 up here and the 102, we can think about those numbers graphically. Okay, you might notice sort of where they came from. They came from taking a population and dividing it by a time. In terms of our picture, that means that we were taking kind of a coordinate on our vertical axis and dividing it by a coordinate on our horizontal axis. What we're really talking about is a slope when we do something like that. Okay, so the 40.6 that we got here, you can think of as being the slope of the line that goes between the 2 points at t equals 0 and t equals 3. Okay, I'm going to label that S1 and then just add one comment here that 40.6 is the slope of S1. Okay, and then similarly, scroll down a little bit, this 102 that we have here, that's also a slope, but it's the slope of the line that goes between the points on our graph between t equals 3 and t equals 4. Okay, so we'll label that S2, and then make the comment that 102 is actually the slope of S2. So what we're really doing here then is comparing slopes when we talk about comparing rates of change. All right, well, let's take a minute just to tie this discussion together. Okay, I want to scroll down to the definition. What we've really been talking about in this problem is called the average rate of change of a function. Those two numbers, 40.6 and 102, are average rates of change. And we can get an average rate of change by doing just what we did above, taking the change in our outputs over the change in our inputs. Okay, if you like function notation, we can also write this as f of b minus f of a. That represents the vertical distance that we changed over b minus a, and that's the horizontal distance that we changed. There's our slope again. Okay, and as we continue through this section, we'll look at some more examples where we calculate this rate of change.